Section 3.2, page 1. Now we're going to look at inverse functions and specifically logarithms. So if you remember, the inverse of a function is a new function itself, and it's undoing the original function. So for example, the function f of x is x plus 5 is undone by the inverse function x minus 5. So notice if I took an input of 1, plugged it into the equation, I get an output of 6. So if I take that output of 6 in the inverse function, I get 1, which was my original input. And that continues, right? -3 in the original function results in an output of 2. And if I take that 2 and put it into the inverse function, I get -3 as my output. My input becomes my output. My original output is used as my input. Now, specifically in terms of log functions, the inverse is the exponential function that we talked about in the previous section. So if I had the function b to the x power, I know we referred to it as ab to the x power, but let's just assume a is 1 for now. The inverse of that function is the log base b of y. Now the reason we say y is, don't forget, we could use y in place of f of x. And same thing, if I have a log function, then its inverse function is exponential, where we keep the same base b, and because we could have thought of this as y equals, we would have this to the y power. And I just tend to think of the function this way. I've got base a, which will stay the base of the exponential form. X is kind of sandwiched in the middle, so x gets to be on its own, and y, who is on its own, becomes my exponent. So if we talk about the graph of a log, we've got this shape down here, a graph that runs along the y-axis and continues to shoot diagonally upward towards the right, or positive infinity. Now the inverse of that function, we already said, was the exponential function, who has a similar shape but is symmetrical about the line x equals y, right? The line x equals y, when x is 1, y is 1. When x is 2, y is 2. And so we get this diagonal 45-degree line of symmetry. So let's talk about some pieces of logs. If we were taking a log function and we were looking at the limit as x goes to infinity, even though it looks like it might flatten out, it does not flatten out. It actually continues on to eventually reach a height of infinity. It basically is boundless. Now, if we were looking at the same log function as x approaches 0, here's our line 0, we only look at it from the right side, which is this side, then the graph is going to reach a limit of negative infinity, so that we have a vertical asymptote where we cannot find a value for 0 from the left. This means the domain, all possible outputs, are going to be x values that are basically from 0 to infinity, whereas the range can have all sorts of different values. So the range the y values can go from negative infinity to positive infinity. And now just to solve a couple problems, I'm asked to evaluate, and generally you're actually not given the equal sign. I've got the log base 2 of 8. Now I think it's helpful to write equals x, because we need to turn around and write the function in its exponential format. Even though it's an inverse of each other, one undoes the other, the relationship to 2, 8, and x is consistent with the inverse relationship of 2x and 8. So when I'm given the question or equation 2 to the x equals 8, maybe you just know 2 to what power equals 8. Otherwise, I suggest you think of 8 in terms of base 2 because this is the base we have on the left. So I left 2 to the x on the left, but for 8, I rewrote it as, 2 times 2 times 2, which is really 2 cubed. And if I have base 2 on both sides of my equal sign, then my exponents are also equal. X must equal 3. So next example, log base 2 of 1/2 equals what value? So I'm going to take the 2 and keep it as a base. I'm thinking of it as equals to x, so that becomes my exponent, and 1/2 goes onto the right side. Now, even though these 2's may feel equal, keep in mind the one on the left is a whole number. It's technically over 1. So I need to pull this 2 to the numerator by rewriting it with a negative exponent. Now I have two sides of an equation that are both a number 2 over an invisible 1. One has an exponent of x, one has an exponent of negative 1. So this statement can only be true, both sides can only be equal, if x is equal to negative 1. And finally, I've got log base 2 of the square root of 2x, and I'm thinking of it as equals x. So this 2 is now to the x power set equal to the square root of 2. But again, I see 2's, but the right side being inside a radical is deceiving, so I'm going to rewrite that radical as a 1/2 exponent. Base 2's are equal, so my exponents of x and 1/2 must also be equal.